feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our work with rational functions. So in the previous lessons, we had worked with rational expressions, simplifying, multiplying, dividing, adding, and subtracting. Now we're going to extend a little bit further and get into rational functions here. Today our focus is not quite yet to rational functions, but is more on equations involving rational expressions and solving those equations. So let's go ahead and get right into some examples here. Problem number one is to solve for the given variable in each of the following equations. So really what we often see is difficult in terms of students' view of solving equations is fractions. Fractions usually start to cause problems for most people. We don't like to work with fractions, and which is okay. In reality, solving rational functions or rational expressions are all about working with fractions, dealing with fractions. In most cases throughout this year, when we have had fractions in our equations, we have found a way to eliminate those fractions. And when we're solving rational expression equations, that process is going to remain the same. So our goal is going to be to eliminate the fractions. Well, how do we do that? If you think about, let's say we had x squared over 2 plus 2x squared over 4 plus 1 over 4. And we wanted to solve this. Well, we would try to get rid of the fractions in the denominators or the denominators here, and so what we would do is multiply by 4, the least common multiple of the denominator, because that would give us a 2x squared plus 2x squared plus 1, and then from there we could go on and solve. Okay, in this case the concept is going to be the same. We chose 4 here because multiplying 2 times 4 would get rid of the fraction, or 2 times 1/2 essentially. Multiplying 4 times 1/4 would get rid of the fractions. So the goal here is to multiply by the least common multiple of the denominators. So if I take a look at problem 1a, essentially I have fractions. Now, the x is not written over as a fraction, but what we can do is we can represent that as x over 1. And we can represent 1 as a fraction as well as 1 over 1. So when we take a look at the least common multiple of these fractions, what we're looking at is the denominators, the least common multiple of the denominators. And we can see that 2 of these have the factor 1, and the other 2 have the factor x minus 3. So if I multiply by the least common multiple of 1 and x minus 3, which is x minus 3, then the fractions will eliminate each other. So essentially what I'm getting is x times x minus 3 plus 12 times x minus 3 over x minus 3 equal to 1 times x minus 3 plus 4x times x minus 3 over x minus 3. That's essentially the process that we're going through. Now, as we would see, some of these x minus 3's would eliminate with one another. And so really how we can write this is we can write this as x times x minus 3. So the x times x minus 3 would be x squared minus 3x. Multiplying 12 over x minus 3 would get the x minus 3's to eliminate, leaving me with just 12. This would equal 1 times x minus 3, which is just x minus 3. And then multiplying the 4x over x minus 3 times x minus 3 would leave me with just 4x. And so now we have eliminated the fractions by multiplying by the least common multiple of the denominator. So the x squared, or sorry, this expression now can be simplified. So what I would do here is get this equation to equal 0. So I would subtract x from both sides, and at the same time subtract 4x. So this would give me a negative x squared minus 8x squared, or sorry, 8x. And then I would add 3 to both sides, so plus 15 equals 0. This would be an equation, quadratic equation that I could factor into x minus 3 and x minus 5. And then I could set both of these equal to 0. X minus 3 equals 0. X minus 5 equals 0. So x would equal 3, and x would equal 5. Now, it is worth going back and checking our solutions because in some instances, we are going to have extraneous solutions. Now, one of the extraneous solutions should be apparent here. If I were to take 3 and put it back into the equation, my first term would be okay. It would just be 3. But if I were to take 3 and put it back into my second term, I would have 3 minus 3 in the denominator, which is 12, which would be 0. So essentially that second fraction here, if I were to input it into the equation, the very first equation would become 12 over 0, which is undefined. So therefore, we know that 3 cannot be a solution. So if I do get a solution that would give me a 0 in the denominator, that solution cannot exist. So I could check my other solutions by substituting in 5. So 5 for x plus 12 divided by 5 minus 3, which would be 2, equals 11. And on the other side of the equation, 1 plus 4 times 5 divided by 5 minus 3, which is 2, equals 11 as well. And so if I substitute in 5, it would be equivalent on both sides of my expression. And therefore, x equals 5. Now, in problem 1b, we could take the same concept here, and I'm going to show you a little bit of a shortcut. So if I have, in this case, I have one fraction on each side of the equal sign. So if I want to multiply by the least common multiple of the denominators, that would be multiplying by both the factors a plus 2 and a minus 1. So what I would get in the first fraction, if I take this fraction times a plus 2 and a minus 1, the a plus 2's would cancel out, and so this would give me 21 times a minus 1. If I multiplied the second fraction by a plus 2 over a minus 1, so if I multiply this one, the a minus 1's would cancel out, and so this would give me 3 times a plus 2. Another way that we can look at this is probably a familiar concept to you guys. When multiplying two fractions to one another, you can cross multiply. So you can multiply one numerator by the opposite denominator, and that will give you two equivalent expressions. So 21 times a minus 1 and 3 times a plus 2. So this works when you have a single fraction on each side of the equation, and only when you have a single fraction on each side of the equation. So this expression can be reached by cross multiplying or by multiplying both of the factors of the denominators. So in either case, when I get to the expression shown here on the screen, I can solve by distributing. 21a minus 21 would be equal to 3a plus 6. And I could subtract 3a from both sides to give me 18a. Add 21 to both sides to give me 27. Then I would divide by 18. So I would get 27 over 18, which reduces to 3/2. So I have a single solution for this rational expression, and it would be 3/2. Now we could go into a method of checking by substitution. The first thing that I would look is to make sure that that 3/2 would not give me a 0 in the denominator. So if I put 3/2 in here, I would not have a 0 in the denominator or there. So far it's good. If you went through the full substitution, you would see that 3/2 is a solution. Now 1c is a little bit more difficult. We've leveled up a little bit here. The concept still remains the same. I want to multiply by the least common multiple of the denominators. In order to do this in 1c, it might benefit us to factor any denominator that we can. So in most cases, we are going to, if a denominator is a polynomial, we're going to factor that denominator. And I can see when I factor the last fraction, the one on the right side of the equation, that it factors into m and m minus 1. So essentially what each of the denominators could become would be m times m minus 1. So the least common denominator, or the least common multiple of the denominators would be m times m minus 1, which I'm going to multiply to each of the two fractions. Now, if I multiply the first fraction, 2 over m times m times m minus 1, the m's would cancel. So I would be left with 2 times m minus 1. The second fraction is going to be subtracted. If I would multiply this one, the m minus 1's would cancel. So I would be left with 1 times m, which is just m. When I multiply the m times m minus 1 to the third fraction, it would eliminate both m and m minus 1, which would give me just 4 on the right side of my equation. Now that I have eliminated the fractions, this becomes a linear equation that I can solve. So I can distribute, combining my like terms, 2m minus m would be just m. Add 2 to both sides, and I'd get m equals 6. Again, I may want to check this answer. So if I'll go through the full process of checking here. If I substitute 6 back into the equation for m and m minus 1 and m squared minus m, I would get 2 over 6 minus 1 over 6 minus 1, which is 5. So this would be the approximate decimal. If I did the same thing for the second side of the equation, I would get in my denominator 6 squared. 6 squared minus 6, which would give me an equivalent expression. So m would equal 6. So we do want to, again, check to make sure our answer does not give us a 0 in the denominator of any fraction, and then we can carry out a full check of that value to see if it is a true solution. Let's continue looking at examples. In problem 1D, again, we have another case where different denominators are going to have different pieces that are going to lead us to a least common multiple. So what we see here is both integers and variables. So first I'm going to consider the integers when deciding what to apply or what to multiply by. In this case, the numbers 2 and 5. The least common multiple of 2 and 5 is 10. So if I can multiply every fraction by 10, that'll eliminate the integers in the denominator. Then if I look at my variables, I have x, x, and x squared, so I'm going to need to multiply by the least common multiple of those, which is x squared. This will again eliminate the denominators and give me a linear equation that I can solve. So if I take 3 over 5x times 10x squared, essentially what I would get here is 10x squared over 5x to simplify, which would give me 2x. So this would be 3 times 2x, and I'd have a minus. If I take the 10x squared divided by 2x, that would give me 5x. So I would have 1 times 5x, which is just 5x. On the other side of the equation, the x squareds would eliminate. So I would have 1 times 10, which is just 10. Now I have a linear expression that I can solve. So I would multiply 3 times 2x, which is 6x. Subtract 5x from 6x, and I get x equals 10. In this case, I could check with my denominators. If I put 10 in for x, that will not give me a 0 in the denominator, and I could continue with a full check of 10 to see that it is a good solution. In E, we see another instance in which we would probably like to factor first. So again, if a denominator has a polynomial, in most cases, you are going to want to factor that polynomial to identify what pieces make up that polynomial. So if I factor n squared plus n minus 6, I would factor this into n plus 3 times n minus 2. Now I can compare the denominators for each of my fractions and see that all of them incorporate either n plus 3 or n minus 2. So the least common multiple would be n plus 3 times n minus 2. So I'm going to multiply every fraction by this n plus 3 times n minus 2. Again, if I multiply both sides of the equation, it's not changing the balance of the equation. So in this instance, if I multiply this first fraction here, the n plus 3's would eliminate. So I would be left with 6 times n minus 2. Then plus, if I multiply the second fraction by that least common multiple, the n plus 2 and n minus 3 both would eliminate, which would leave me with 20. On the right side of the equation, I would have the n minus 2's that would eliminate, which would leave me with 5 times n plus 3. Now I can simplify by distributing the coefficients of my binomials to get 6n minus 12 plus 20 equal to 5n plus 15. Combining like terms on the left side of the equation, I have 6n plus 8 equals 5n plus 15. Then I could subtract 5n from both sides, subtract 8 from both sides, and I would get the solution, n equals 7. Again, I want to make sure that that 7 would not give me a 0 in the denominator. So 7 plus 3 is 10, that's fine. 7 minus 2 is 5, that's fine. If I get 7 squared plus 7 minus 6, this would be 50, so I would not have a 0 in any of my denominators. I could continue a full check of the equation if I wanted to by substituting n into each fraction, 7 into each fraction, and I would find that I have the answer here. So after we eliminate the fractions, we have linear equations that we can then solve, in most cases, sometimes polynomials, that we can then solve. And then we want to confirm that the answer that we have reached does not give us a 0 in the denominator. As we know, you cannot have 0 in a denominator or divide by 0. And this looks like a good place to stop. So we only found one extraneous solution in our solving process, but we have fully practiced this solving process, this concept. The goal in solving equations with rational expressions is to eliminate the fractions. Then we either have a polynomial linear equation or some kind of polynomial equation that we can solve using techniques that we've learned throughout this year. Again, as always, it's good to check your answers, but we do want to make sure we double check to see that our solutions would not give us a 0 in the denominator. If they do, in the case of 1a, then this would be an extraneous solution. So this is a good place for us to stop. When we reconvene in class, we will continue to work on some practice problems and go over any further questions that you guys have. As always, thank you guys for tuning in, and I'll see you soon.